We start, I'd like to remind you, we have a midterm next Tuesday, and the procedure is outlined in my previous email. And this will be open book, open notes, but closed internet. I don't think you can search and find the answers, but it is understood that you are not do searching while you take the exam. And we will do it at the class time. So from 12:40 to 2 p.m. And I'll allow you about 10-15 minutes to upload your answer to B courses. I will create the assignment. And so that's the basic procedure. If you have any question, we can discuss it now. I understand it is harder to do interaction during the Zoom lecturing. So I welcome you to use the Piazza. Previously, we have not used much Piazza. I encourage you to use Piazza for discussions, and the GSI and I will try to answer Piazza as frequently okay, let me see if anyone is typing any message. Okay, there is a question, what contents will be covered in the midterm? So midterm area will cover basically from week 1 to last Tuesday. So materials will be all the way to last Tuesday. So micro resonators. So up to micro ring resonator. Okay. So if there's no further question, today we like to resume where we stopped before we branch out to talk about waveguides, passive optical components, and building blocks for photonic integrated circuits. So before we break for that, we were talking about optical transitions. So we'll be back to talk about active optical materials, optoelectronic materials. So before we break, we were talking about Fermi golden rules, which talks about the governing physics for a two-level transition. And there are really two parts. One is absorption, and the other one is emission. Okay. And the absorption is given by absorption probability is given by 2 pi divided by h bar square, and there is a matrix element HFI prime square. So if we call one of them is initial state, the other one is final state, and the matrix element is the perturbation introduced by a photon that connected these two states that are otherwise independent. And there is a conservation of frequency here. And this is Fi, omega Fi minus omega. Okay, this omega is optical frequency. And this omega Fi is the difference of electronic state energy. Electronic states energy. So that's basically a statement of conservation of energy. And we can do change of variable. Sometimes it's more convenient to discuss in terms of energy rather than frequency. So energy is equal to h bar omega, as we all know, through the basic quantum mechanics. So essentially, we need to do a change of variable. I don't know when is the last time you think about change of variable for delta function. Let's review it here. So change of variable for delta function, delta x. So if we have a delta function, now that's a multiplied by x. Well, if you think about just the definition of delta function, it's infinite when x equal to 0 and the 0 otherwise. It seems it's the same if you do integration of with a variable that's linearly scaled by a factor of a. But it turns out if you do more detailed investigation, there is actually a factor coming out due to change of variable. How do you think that? Basically, you have to think delta function in terms of the integration of usually with another function, delta x dx. And so in this context, you can easily derive this change of variable here. So which means if we do a delta of energy function, which is delta h bar omega, and this is going to be equal to 1 over h bar delta omega. Okay, so if we substitute and convert this absorption transition rate, so we will have WABS absorption is really equal to 2 pi over h bar, no square. Okay, same matrix element, HFI prime square, and now we have a delta function of electron energy minus Hall energy minus h bar omega. Okay, so this will be our absorption probability, and now we are calling the energy in the upper level E, and the lower level will be from valence band, so that will be EH. Okay, and by the same token, we will have emission. This will be stimulated emission. In this case, electron will be transition from the upper level to the bottom level, and in the process emit the photon that's coherent with the incoming photon. For stimulated emission, in our last lecture, it's the same Fermi golden rule. The only difference is just in the delta function. Okay, so the emission process is basically same 2 pi over h bar, and h, let's change, well, let's call this FHI square. And the delta function will be now, it's actually the same, the energy conservation, EE minus EH minus h bar omega. Okay, so in other words, they are really same strength. The strength of absorption is equal to the transition rate of emission. Okay. Any questions here? So this is basically the same as the two-level system we discussed from last time. So Now let's go from two-level system to a band in semiconductor. Okay. Intuitively, basically, you think of two discrete levels. These are described by what we just described. And in a semiconductor, well, you have conduction band. So there are many, many of these states, energy states here, okay? And altogether, this is a conduction band. And in the same picture, there are many, many states here, and collectively, they are called valence band. And as you could envision here, many transitions are possible. You can change from one energy state to another. You can change, slightly different higher photon energy. You will be absorbed from a lower energy level to a higher energy level. And likewise, the emission process, there are also many, many different possible bands. So to calculate the entire transition, we will therefore need to sum over all possible energy state transitions. As we discussed in the third lecture, basic properties of semiconductors, it is more physical to describe this phenomena in the K space. So in the K space, we have conduction band, which is represented by a parabolic curve, okay? And valence band, represented by a similar curve, okay? This is K. And we will be looking at, for example, for a particular photon energy, let's say we'll be looking at the photon energy corresponding to this transition here. Now we have many states that needs to be summed over, okay? And these states in this simplified two-dimensional plot will be occupying kind of a ring here, okay? Likewise, the whole will be occupied by a ring. So there are many different states involved in this transition. And previously, we have also shown that because photon momentum is so much smaller than electron and the whole momentum, so we basically say, well, the conservation Kc and Kv needs to be conserved. They need to be the same. Okay. So with that in mind, we can rewrite the transition rate. The transition rate will be, let me move it over here. The transition rate from valence band to conduction band, okay? This will be the summation process. We have done that before. It's basically 2 over V that we sum up all the K space with Kc equal to Kv, okay? And the transition strength is 2 pi over h bar. And let me rewrite the matrix element to HCV, okay? So now the final state is conduction band. Initial state is valence band, okay? And there's a delta function of E minus EH is equal to h bar omega, okay? Now, in semiconductor, we also need to consider the occupation of the particular state. In order for the absorption to happen, the conduction band needs to be empty and the valence band needs to be occupied. So we need to multiply by basically the Fermi Dirac distribution here. The valence band has to be occupied, okay? And conduction band has to be empty. This is represented by Fv and the 1 minus Fc. So again, Fv is a number between 0 and 1, is basically the probability that valence band, that particular valence band state is occupied. Okay, and that's the premises for absorption. And 1 minus Fc, similarly, is the probability that the conduction band state is empty. So there's a place for the electron to land after the transition. So this is a whole band transition. The only constraint is the energy difference is equal to photon energy. And then you sum over all the states, you will get the total absorption rate. Okay. And similarly, okay, I see a questions here. Why is it not h bar omega minus EE minus EH? So there is, so the question is, why not? I guess the question comes a little bit earlier. Let me write it here. So I guess the question is, why not delta h bar omega minus EE minus EH? Okay, so delta function actually, delta minus x is equal to delta x. So these two are the same. They are all related to, they are just just conservation of energy. And what is the variable R B2C stand for? Okay, so the physical meaning of this variable is total absorption rate from valence band to conduction band with for photon energy equal to h bar omega, and this absorption rate is per unit volume. So that's why you see the factor here, 2 divided by V. And these two, again, are accounting for spin. And this V, as we have experienced before in the derivation of the density of states for electrons or for holes, these are the volume which will cancel out as we do the summation. Okay, follow-up questions again on this here. So why is this expression look different from what we had before? Okay, so before in our discussions, okay, in previous lectures, when we discuss absorption, we have I, F, and when we discuss absorption, it's like this. but we switch the label when we talk about emission. Okay, so this become emission. Here we are going to talk about both absorption and emission together. We're going to mix the equations together. So we have fixed the energy state label. We don't swap the energy state label here. And another question, why do we need to assume Kc equal to Kv? So why do we need to assume Kc over Kv? So for optical mediated, for photon mediated transition, we basically have K electron, if it is an absorption, will be equal to K, let me be consistent, E in the conduction band from valence band plus K of photon. And because K photon is much smaller than both electron and hole, so we are dropping, we're dropping the photon wave vector. So basically we say this transition is always vertical. So this transition here, for all practical purpose, it is a vertical transition. Okay. Phonon can assist. So you are talking about a follow-up question is what about phonon assisted transition? So yes, that's another possibility with, let me switch pen color again. What about phonon assisted transition, optical transition? Yes, this does exist. Most well-known example is, of course, silicon. And silicon, the EK diagram looks like that. And conduction band electrons are here, and valence band holes are here. So the transition would happen, basically the electron would jump to a virtual state, and then with a phonon, phonon does have very large momentum that you can do this indirect band gap transition. This does happen, and that's the reason our camera work. Our CCD camera are all made of silicon pixels, and silicon pixel in the visible light, in the red and green light, it's an indirect band gap transition. But generally, this process is much weaker than direct band gap transition. Okay. So as a result, it's very difficult to make this into a laser, for example. Okay. This hasn't stopped the people from trying, and there are some sort of limited success, but in general, this is a very difficult process. It involves 3 particles now, in addition to electron hole pair and photon. Now you need a phonon. So you could imagine the probability will be much reduced. Okay, the next question. Need to take into account of phonon occupation. Yes, so and you will be affected by the phonon population. So we will not get into that detailed discussion, but for direct band gap, there's no phonon involved, so we don't need to include the phonon probability. Let me see if I read your question correctly. We need to take into account phonon occupation. So direct band gap, no. Indirect band gap, yes. It's become really complicated. And so here, yes, here we are just considering direct band gap semiconductor to first understand the principles. And after we understand the principle, we could do kind of qualitative extrapolation to more general cases. Okay. So now we're going to write a similar equation for emission. So emission will be basically from conduction band to valence band. And again, these are absorption per second per unit volume. And we have to sum over all the volume. So these are basically same summation. Okay, Kc equal Kv. So Kc and Kv are not independently variable. So this is a single summation rather than double summation. And we have 2 pi over h bar, and same matrix element as we learned from earlier perturbation theory, Fermi-Golden rules. The downward transition and upward transition have same matrix element. Okay, same energy conservation here, EE minus EH minus H bar omega. Now the probability, occupation probability, will be the opposite. In order for emission to happen, we need to have conduction band occupy. So simple Fermi Dirac distribution here. Valence band needs to be available. Otherwise, Pauli exclusion principle will forbid that transition to happen. So we will have 1 minus FV here. Okay. So far, so good. Any questions on this? Okay, so now to combine the two, we like to have net absorption rate. Net absorption rate for the entire conduction band and valence band per unit volume. Okay, this is simply you subtract the downward transition from upward transition. So the net transition rate is basically R V to C minus R C to V. And you observe these two equations. The only difference is in the population probability. So this is basically equal to 2 over V and sigma, again, Kc over Kv, and 2 pi over h bar, matrix element square, and conservation of energy. And you'll find the product term cancels out. So this simply becomes Fv minus Fc. So it's actually a simpler expression here. Okay, I'm reading the question now. Why in the previous discussions we did not consider Fc and Fv? So this is our two-level discussions when we derive the Fermi-Golden rule. And remember, in our perturbation theory, our initial condition, okay, so previous discussion, we have assumed initial condition that is C Ci, all electrons are in the conduction band. So we assume the coefficient Ci, I forgot if I use the same symbol, but Ci t equal to 0 is equal to 1. And the C, the probability at t equal to 0 is equal to 0. So in other words, we already assumed the equivalent of FV equal to 1 and FC equal to 0. That's how we derive that perturbation theory, if you recall.
So previously we only considered the situation okay.
Sorry, I didn't. Your question did not come through entirely. Can you repeat it?
Yeah. So previously we only considered the situation in 0K.
So in two-level system, there's no summation. There's only two states, so no summation needed. There's only two states. Okay, so that's why there's no summation involved here. Why do we have to do summation here? There are so many states in the band, and therefore we need to sum up all the transition. Some of the transition are from different states, but they have also the same frequency. Okay, so we need to sum up all the transition that has the same energy difference but different case. That only exists in semiconductor. Okay, or I should say more strictly, only existed in a crystal, in the solid state media, where there are bands of states. Okay, all right. So now we have a net transition rate. Again, the net transition rate is the transition per second per unit volume. What we often need is absorption coefficient. Okay, so what experimentally measure? Is absorption coefficient. Okay, what's the reason not to measure the absolute transition rate? This is net transition. Okay, so let's write it again. These are net absorption. So these are really, well, to be even more precise, these are number of photons absorbed per unit volume per unit time. So that's this quantity here. Now, this obviously is proportional to the incoming light intensity. If there are stronger intensity, you will observe more transition. But the absorption coefficient is a quantity that's independent of intensity. That's more a material property. So that's obviously more desirable. Why is this transition rate dependent on incoming photon intensity? Well, it's sort of hidden in this matrix element. This matrix element, if you recall, it's a dipole moment. It's actually proportional to the electric field, optical field, square. So stronger field, more absorption. Okay, so we like to kind of have some sort of normalization, and that's what the coefficient, that's what this absorption coefficient comes in. Absorption coefficient is generally defined as intensity. This is optical intensity, okay? in a media. So after it enters the media, propagating in the direction of Z, this is optical intensity. It will decay exponentially. So you will follow exponential minus alpha Z. Okay. So mathematically, this means I0 exponential minus alpha Z. And alpha is the number we call absorption coefficient of the media. Okay, what is I of Z? I of Z is what we call optical intensity. Intensity, roughly speaking, is a square of optical field. More precisely, this has the unit of optical energy. So the unit is actually optical energy, joule per meter cube times speed of light, meter per second. So this is the amount of energy per unit area that's moving at the speed of light, so per second. So that's the unit for optical intensity, okay? And we can actually, based on this physical understanding, we can actually write what is I of Z, okay? So I of Z is actually equal to the intensity, the energy intensity. Energy intensity is basically 1/2 epsilon E square, here is optical frequency, optical field, times the speed of light in the media. So N is the refractive index, okay? And epsilon is epsilon 0, epsilon R, E square divided by 2, and C over N. And generally, for optical material, epsilon R, if we consider just the real part, is actually equal to N square. So we can substitute that. This becomes epsilon N square E square over 2 C over N, or this is epsilon N E square times C divided by 2. Okay, so this is I of Z. Okay, so we can relate this quantity to absorption rate of photon per unit volume. What is absorption rate per unit volume? Well, let's consider we take a slice here. So we consider photon entering into Z, okay? And we measure again the number of photons at Z plus delta Z. So this is remaining photon. So these are the photon that's absorbed, okay? So photon absorbed, so number of photons absorbed will be equal to I of Z minus I Z plus delta Z, okay? And divided by delta Z, okay? I itself is per unit volume, and you divide it by the longitudinal dimensions. So this is basically joule per meter cube, okay? And we would like to convert it to the number of photons, since that's what's in the R expression earlier. So we normalize this to photon energy, h bar omega, okay? So this is per second here, and multiplied by 1 over joule. So the unit is dimensionless, basically means the number of photons per meter cube per second. Okay, that would be the unit here. All right. And so this is, we can estimate these easily. The numerator is basically di dz times minus di dz times delta z divided by delta z. That's the first term. Second term still here. And this is basically, first term is really alpha I of z is exponential dependence, delta z divided by delta z, and 1 over h bar omega. Okay, so delta z cancels out. Okay, and this we can rearrange. So alpha is basically equal to this expression here is R. This is number of photons absorbed per unit volume. Okay, so this is R, basically R divided by I divided by h bar omega. Okay, or R times h bar omega divided by I. Okay, and this is R divided by I, which is epsilon 0 n e square c and 2, let's move 2 over here. Okay, so this is the expression for alpha. So it's basically proportional to R, but we normalize it to the incoming intensity. So the E square will cancel out the E square dependence in the matrix element. Okay, so this will give us a net material property, absorption coefficient. So we plug in the expressions before and simplify the denominator and numerator of the coefficient terms. So we basically have h bar omega, and here is 2 h bar omega epsilon 0 n e square c, okay, times the expression for R, that will be 2 over V sigma, this Kc equal to Kv, and 2 pi over h bar square, no square, h bar, and hcv prime square, energy conservation, E minus EH minus h bar omega times F V minus FC. Okay. And we can simplify this expression a little bit. First, we recognize that, well, this matrix element, in principle, you need to calculate the matrix element for every state. But since for optical transition, basically we'll treat this like a constant. Because all the states are near bandage. So because all the states of interest are near bandage. What happens if this is not the case? If you have photon energy that's much, much higher than the band gap, well, this term will change slightly. The correction will be needed, okay. And FV minus FC, actually for optical transition, as we will see later, this is actually independent of Q. K. So this term is also independent of K. And we can move it out of the summation, okay? So we move this constant term out, okay? And this will become a function. So this will become H bar cancels out, H bar cancels out, okay? And so we have 4 pi omega divided by epsilon 0 and c. Let me write E square here. And then we have this term 2 over V sigma K sum over K, but Kc is equal to Kv, okay? And we have basically delta function EE minus EH minus H bar omega. And let's take FV minus FC also out of the summation, okay? So it breaks up to 3 simple parts, okay? The first part is basically just a constant, okay? And the last part is a population factor, how much states are occupied by electrons and holes and so on. So only the middle term is kind of related to the number of states available in the semiconductor. So these are number of electron, not just electron, but electron hole under the condition of Kc equal Kv, okay? Number of these states per unit volume, okay? We have estimated this problem before. Basically, when we calculate the density of states for electrons in the conduction band, we have seen this problem before. Let me read the question. The constant for the perturbation okay, lots of questions. So the question, most of the question is why is this? Why is FC minus FV independent of K? Okay, so I'll promise to look at this, promise to look at this next. And the next question, where did it go between the last 2 lines? From here to here? From here to here? I basically move out this 2 pi over H bar. I move these population related quantity out of the summation. So basically, I'm only summing over the conservation of energy term. What about the constant of perturbation? Oh, sorry, I did miss that. I should add it here. These are not eliminated. CV prime square. Thank you. Okay, so let's deal with this middle factor here. Now, if you recall earlier, we talked about density of states, okay? So earlier, we talked about density of states for conduction band as well as valence band, but we mainly derive conduction band. Okay, how does this work? Well, this says, well, in the conduction band, here's a conduction band in the K space, okay, E, okay, and for a particular electron energy, so here, E, um, EE, EE is equal to EC plus 2ME star H bar square K square. Okay. So if we want to find out this electron energy, how many states are like this in the conduction band? That basically is 2 over V summation of all possible K such that the energy of the electron is equal to this particular electron energy here, all right? And we derive through these by physically counting the states in a shell in a hemisphere in 3 dimensions. We convert this into an integral of density of states, and we integrate over the density of states. Okay, so this is electron density of states. Okay, and basically, we are counting the K space, right? So you can see what we have here is E minus EC. This is equal to 2M E star H bar square K square. And we're basically counting states in this expression here. This is very similar to counting free electron density of states, okay? And we have derived rho E as a function of energy, EE. This is equal to 1 over 2 pi square and 2ME star divided by H bar square to the power of 3/2. And these are all constant. The most important term is the last term. This is E electron energy minus conduction bandage. Okay, so in other words, the density of states for electron, rho of E versus E, it's a square root dependence here. So this is proportional to E minus EC. So there's no energy state until electron energy is greater than conduction bandage, and then it's a square root dependence. Okay, all right. So now if you compare with what we need, it's very similar to this expression. What we have now, instead of just one electron, we will be considering electron and hole transition. So they are bound by this vertical line, okay? And here we have E, we have E, H, okay? And EE is equal to EC plus 2ME star H bar square K square, okay? And EH is equal to EV minus H bar square K square divided by 2MH star, okay? And if you subtract these two equations, you will have EE minus EH equal to EC minus EV plus, really, these are the same factor here, 2 H bar square K square, and it was 1 over M E star plus 1 over M H star. Okay. The first term for conservation of energy is really equal to h bar omega. So this is h bar omega. EC minus EV is basically band gap energy. So the third term, we will introduce a reduced effective mass. Of electron hole pair. Okay, this mass is neither of electron nor of hole, but two of them combined together through this conservation of momentum. So 1 over m r star is equal to 1 over m e star plus 1 over m h star. So this is two particles kind of tied together, and you are treating both particles as combined systems. So I asked this question before, and I think you have answered this question beautifully. If we have two particles, this mechanical analogy, okay, let me draw it here. So the mechanical analogy is basically you have two particles, okay, and they are traveling with different velocity. This is m1, v1, this is m2, v2, and if you are interested in their combined center of these two mass and traveling with a combined velocity. These equivalent particle, 1 over m here, so 1 over m is equal to 1 over m1 plus 1 over m2, okay. So here, the electrons and holes are bound by this requirement of that their momentums needs to be roughly the same. And that's why we are able to reduce it. If they are not bound by the optical transition, then they are no longer bound by this. The electron energy state can be arbitrary, doesn't need to be the same. So this only applies to this particular case. Now, if you rewrite this equation, okay, that is h bar omega minus Eg is equal to 2mr star and h bar square k square. Okay. Now, if you compare this equation with the electron equation, whoops. Okay, if you consider this equation with this electron equation, okay. An important thing is to kind of recognize the right-hand side. The right-hand side is basically the same, except the effective mass is different, okay. It's all quadratic dependence. So when we are counting states, we're basically counting the number of k states that's available in the momentum space. So without derivation, I can simply write these effective reduced density of states. Okay, so this is what we call reduced density of states. To be basically rho, and we call this r. It's a function of h bar omega, just like the previous equation. It's a function of electron energy. The electron energy is now replaced by photon energy. Okay, and the constant will be the same because we'll go through exactly the same counting in the hemispherical shell. Okay. And the only difference mass will be replaced by 2mr star, okay, h bar square, similarly to 3/2, and the square root is the left-hand side of the equation. So the left-hand side of the equation is h bar omega minus Eg. Okay. So this is the joint density, reduced density. This sometimes you will also see, this is also called joint optical density of states. But this name is both good and bad. Good, it tells you this density of states are joined optically. But these are actually electronic density of states. So don't forget, this is really an electronic density of states. Okay, that's why it has a similar density form as the electron density of states. Okay, so the expressions now become very simple. We really have reduced alpha to this constant 4 pi omega, okay, 4 pi omega HCV prime square, and epsilon NC, epsilon 0, NC, and E square, and everything inside the bracket will become reduced the density of states, and we have the population factor. So here will be rho R and H bar omega, and we have the term F V minus FC. Okay. So let me see. There is a question. I'm not sure whether ME star is the same for all the energy levels in the conduction band. Yes, this is true. So the question is here, is ME star constant? Well, yes, under effective mass approximation. So these are basically the approximation assumption. Under this assumption, the whole band just have a constant ME star. We did mention this is a very good approximation for all the electron states near the band edge. Practically for most of practical devices, lasers, detectors, and so on, or electronic devices, these are reasonably good approximations. For some devices where people are interested in very high energy electron injection into the conduction band, you start to see the departure from parabolic curve. And again, corrections are needed. So for most of our fundamental theory we're going to cover in this course, we will stay close enough to the band edge so that ME star is a reasonable constant. Okay, all right. So the last part is to investigate the matrix element. Okay, so HCV prime square. Okay, so previously we have looked at dipole approximations. Dipole approximation will say, well, the perturbation is really introduced by a dipole. A dipole is charge times the spatial coordinate vector times the the force caused by the optical field. Okay, so this is dipole moment. Basically, this is the dipole moment. Divided by 2. The divided by 2 comes from the real part. We only take the real part of the exponential formulation. Okay, so using this approximation, HCV prime square will be equal to basically Q square times E square divided by 4, okay? And I have extra E here. Actually, I meant to use, this is E cap, and this is E scalar. So E cap is the vector direction of the optical field, which we call polarization. Which is basically the direction unit vector of E. Okay. So I can take E out, and the square will become E cap times R CV square. Okay. R CV is basically the integral of conduction band times R times valence band integrate over space. Okay, so well, these are still symbolic. We still need to evaluate this integral, which we will not do without going into the complex form of the wave function. But without doing that, we can now clearly see the E squared dependence here, okay? So when we combine into alpha, that term will cancel out, and alpha will simply becomes pi omega q square divided by nc epsilon 0 and times rho r h bar omega and times fv minus fc. Okay, so this is a very simple expression, and the first factor is simply a constant. So let's call this constant C1. Okay, it's mildly dependent on frequency. There is omega dependence here, but for the range of frequency we are talking about near the band edge, we can treat this pretty much as optical frequency corresponding to the band gap energy, so roughly constant. Okay, and if the semiconductor is undoped, is undoped ideally and unbiased, we don't apply any voltage across it, either forward or reverse, then generally FV is fully occupied. So FV is equal to 1, FC is equal to 0. It is just unbiased. So all the states are fully occupied in the valence band. And in this case, FV minus F is simply equal to 1. So at this point, you get maximum absorption. And your absorption coefficient, the spectral shape is basically the shape of your reduced density of states. So if you treat your absorption coefficient alpha as a function of h bar omega, and here is for omega, the photon energy, your absorption curve is square root. This is C1 rho r of h bar omega. And this is proportional to square root h bar omega minus bandgap energy. Here is EG. Okay. Okay, all right. So now when the semiconductor is biased, okay, so if semiconductor is biased, sometimes we call this is a pumped. That's a terminology often used by the optoelectronics community. Okay, then FC minus FV is usually less than 1. Okay, FV minus FC is less or equal to 1. Okay, so you'll get somewhat reduced density of states. Okay, what is FV minus FC? This requires a little bit more discussion. I think we will run out of time today, but let me just plant an idea for you to think about. So we have conduction band, we have valence band, and if we allow us to think about pumped case, bias case, we will have quasi-Fermi energy, Fc. We have quasi-Fermi energy, Fv here, okay? And we are considering an optical transition absorption, either here, or maybe here, or maybe here, okay? So for Fermi distribution, let me draw it here. So this is energy, and if I draw FC, FC is a Fermi direct distribution. So it has a distribution that looks like this, okay? Here is 1, here is 0, and exactly in the middle is 1/2, right? And if I look at the Fermi direct distribution for holes, okay, so here is FV, and if I draw my axis of FV, it has a similar distribution. It's also between 1 and 0, and in the middle is exactly 1/2, okay. We will show in a little bit more detail next time, but I kind of intentionally draw when the electron energy is right at the Fermi level, the whole energy is also exactly at the Fermi energy. This is actually quite easy to prove under effective mass approximation. We'll go over that next time. You're welcome to try to prove it yourself. So we can separate this into a few cases. One, when E is greater than Fc, so that will be the case here. EE is higher than Fc, but because they are electron and hole are bound by this straight line, when this is satisfied at the same time, EH will be lower than FV. Okay, so here is EH, right? So we'll be talking about electron is occupying in this part of the Fermi direct curve, whereas hole is occupied in this part of Fermi distribution. There's no vertical line here. This is not momentum. The vertical axis is Fc and Fv. Okay, so you can clearly see here, Fv minus Fc will be greater than 0. Okay, and in the case of EE is equal to Fc, you can prove under effective mass approximation, EH is equal to Fv, and in which case Fv minus Fc will be 1/2 minus 1/2. This is exactly equal to 0. In the third case, so this is 1, 2, 3. In the third case, EE is now below Fc, and by the same token, EH will be now higher than Fv. In this case, Fv minus Fc, so will be somewhere between these two crosses. So this will be less than 0. Okay, so without writing the expressions, I can conclude that my Fermi factor, so this quantity Fv minus Fc as a function of h bar omega is related to basically key parameter that is EC minus EF. When the photon energy is greater, the Fermi energy is 1. Okay, so case 1, that is here. Yes, so case 1 is here. Okay, and case 2 is 0. Okay, case 3, when it's far below, is -1. Okay, and they're kind of connected smoothly here. So this is the Fermi factor here. Okay, so Fermi factor has play a central part on when the material has absorption, and when it is biased hard enough, the absorption could become negative and you start to have a gain. And that's the origin of semiconductor gain. Okay, EC and EE. So E, did I write? Okay, this should all be EE. Okay, so thank you for pointing out the discrepancy. This should all be electron energy. Okay, all right. Any more questions? So time is up. I'll stop here. And again, next Tuesday, watch out for a link mostly coming out through B courses. I'll give you more specific instructions, and we'll have online exams. Okay? And feel free to use Piazza to ask questions. And meet you next Tuesday.